Now let's work on Chapter 6, Electronic Configuration, question number 3. The electron configuration of an iron atom is 1s2, 2s2, 2p6, 3x2, 3p6, 4s2, 3d6. So basically the electron configuration is already given. What we need to do is to determine the number of unpaired electrons in the iron atom. Okay, so first let's count the total number of electrons. If you count from here, that's 2, 4, 10, and then 12, 18, 20, 26. All right, so from that electron configuration, we know there are 26 electrons. All right, okay. If it's not given, let's say, the electron configuration, how do you find out the number of electrons, of an atom, any atom? First, you find the element in the periodic table. So in this case, iron, okay, that's number 26. What is that number? That is atomic number. That equals the number of protons. And that happen to be also the number of electrons, because each proton carries positive 1, each electron carries negative 1 charge, so that the atom or the element stays neutral charge-wise. Okay, 26 electrons. That's what we know. Okay, from previous lectures, you also know the electron configuration. You start with the lower energy level. In this case, of course, that's 1s, then 2s, then 2p, and so on and so forth. So each s orbital can accommodate 2 electrons. Each p orbital can also accommodate 2 electrons. You need to remember, any orbital, one orbital can only accommodate 2 electrons maximum. But how many p orbitals are in there? We have 3 p orbitals. Then each have a maximum. That should be 6. That's why here you have 2p6. 3p6, the same thing. And the s, again, you just have 1 s orbital. So therefore, 1 times 2 should be always maximum of 2. Doesn't matter what the principal quantum number n is. 4s, 2 electrons. 3s, 2 electrons. 2s, 2 electrons. 1s, 2 electrons, and so on and so forth. Okay, so for s orbital, you have 1. For s shell, you have 1 orbital. For p shell, you have 3 orbitals. Then how about d shell? So now, let me see, probably you can't see in there. Okay, so how about d shell? How many orbitals are in there? 5. And each orbital, let's say maximum, that can accommodate a total of course 10 electrons. But you may not have that many electrons to fully fill the 3D. All right, so therefore, that's what we are going to do now. We are going to determine, okay, the numbers of unpaired electrons in iron atom. So in other words, we need to see how many unpaired electrons will end up, so in this iron atomic electron configuration. Okay, so now we know there are total 26 electrons, and up to here, how many electrons are in there? 20 electrons. All right. So therefore, we know those are all fully filled, those lower energy level. And remember, the 3D, its energy because of the penetration of the 4s electrons. So the 3D's position is a little bit further away from the nuclear than the 4s electrons. All right. In other words, the 3D's energy is slightly higher than the 4s energy, as I showed you when we solved the previous problem, when we solved question number 2 in the same section. I showed you this, if you still recall that. And as you can see, okay, so that's a 3s, 3p. Right after that, not 3D though, you see it's a 4s. Energy level is lower than the 3D. So therefore, the last 6 electrons should fill these 5 3D orbitals. All right? So once we have done that, we should be able actually then to tell how many unpaired electrons. So you see? So that's the strategy. Okay? Good. Now, we just mentioned there should be 5 3D electrons. No, orbitals, I'm sorry. So 5 is what I'm going to do. 1, 2, 3, 4, 5. Okay, and that's the 3D orbitals. So you have, of course, 5 different 3D orbitals right there. If you want to know the details, it's, that should be, you have a 3DZ2, 3DXZ, 3DYZ, 3DXY, and 3D x squared minus y squared. Okay, so you don't need to memorize the specific name or or the symbols, for the each individual orbit. Okay, but you do need to know those are 5 different ones. They should have the same energy. The only difference between those is just the 3-dimensional orientation. You see the dz squared obviously is along the z-axis. All right, dxz is obviously the orientation is along the xz plane. That's 2-dimensional, and so on and so forth. But in order to solve this problem, you don't need to know all of this. What you need to know is there should be 3D orbitals. And then you also need to know the Hans rule. Okay? So 6 electrons remaining. You see, we have a total of 26, and now 20 already. 26 minus 20. You see up to a 4s2, then we still have 6 electrons remained unassigned. According to Hans rule, remember the Hans rule. What does it say? Okay, if you have the same, for example, the 3p orbitals, or the 3D orbitals, or even 4f orbitals. So all of those orbitals, they are identical in terms of energy. So only the orientation is different. So therefore, whenever that's the case, Hans rule tells us they occupy each orbital with 1 electron, a single electron, and all of those electrons in each orbital should have the same spin. the same spin. You see, that's why let's say we'll put everything spin up. And now we already assigned 5. We should have a total of 6. So 6 minus 5, we still have 1 electron remaining unassigned. Then we go back to Hand's rule. Okay, after they are all assigned singly with the same spin, then we go back to the first one we just paired, but has to be a different spin, the opposite spin. And now let's count the number of unpaired electrons. 1, 2, 3, 4. What is asked in the question? Oh, it's here. So determine the number of unpaired electrons. So therefore, the unpaired electrons, that should be 4 unpaired electrons. That's this 4. 1, 2, 3, 4. That's question number 3.